Hello, and welcome to another Von Carmen lecture series, Rising Tides. I am Nikki Wyrick from JPL's Office of Communications and Education. Tonight, as we approach the one-year anniversary of NASA's Earth flagship mission, Sentinel-6 Michael Freilich, we will take a look at how we study our oceans, our planet, and what is coming next. Joining us as co-host fielding your questions this evening is Earth Public Outreach Specialist, Jocelyn Argueta. Hi, Jocelyn.
Hey, Nikki. Great to be here tonight. And I want to take a moment to just remind all of our viewers that this is your space program and we want you to be involved in the conversation tonight. So, from wherever you're watching this, feel free to add your questions to the chat. Our amazing social media team is going to get those questions to us and we'll try to get through as many as we can. And if for whatever reason you don't see the chat, just hit refresh and it should come right up.
Awesome. Thank you, Jocelyn. We're so glad to have you with us this evening, fielding all those wonderful questions. Just a reminder to all of you watching this evening, if we do run into any technical difficulties, we do ask that you stick with us as we get these sorted out. Now, our speaker this evening, Dr. Josh Willis, is the lead NASA scientist for the JASON and Sentinel-6 satellites, which measure sea level from space. He is also the lead scientist for NASA's recent airborne mission, Oceans Melting Greenland, or OMG. Josh will discuss these missions and how understanding and predicting sea level rise is one of the most urgent problems in climate science today. Hi, Josh. How are you doing tonight?
Hi, so good to be here. Thank you.
We are so happy to have you, and I'm going to turn it over to you because you've got a lot of great information to share with us tonight.
Fantastic. Well, thank you so much. And I just want to say before we start, if you're watching this live, it's Veterans Day, and I'd like to take a moment, if you're a veteran, whether you're watching live or not, to thank you for your service. So let's get started. Why am I here? Well, I'm an oceanographer and I study the oceans using data from NASA satellites of all different kinds. But as Nikki said, I'm also the lead NASA scientist for the Sentinel-6 and JASON missions, which measure sea level from space. So what I really want to talk to you about tonight is climate change, or the warming of our planet. Now, when we think of the planet warming, we typically think of the atmosphere warming. And that's what this first graph that I'm going to show you tells us. Now, I promise I won't show you too many plots like this, but if you'll bear with me, on the bottom axis we have time. This plot goes back to the 1880s, and what we have on the vertical axis is temperature, and this is not just any temperature, it's the average temperature of the entire planet. And this tells us a very simple story that the Earth is getting warmer, and it's getting warmer pretty fast. A degree of warming, a degree Celsius of warming may not seem like a lot, but it's actually a huge change to our climate, and it's happening right now. And the big question, of course, is why? And the answer is actually us. We are actually warming the planet's climate by adding carbon dioxide to the atmosphere and increasing the amount of heat that we trap from the sun. Now, if we look back in time at the record of carbon dioxide since about 500,000 years ago, it looks something like this, where you can see carbon dioxide's gone up and down for about every 100,000 years. And right now, we were actually in a warm period. About 20,000 years ago, we were in a cold period and carbon dioxide levels were low on the planet. And then it started to warm up. Naturally, it warmed up, and we've been in a warm period for about 10,000 years. And during that time, CO2 increased in the atmosphere, and we trapped more and more heat. But if you look back at the last 500,000 years, carbon dioxide today is higher than at any time in the last 500,000 years. And the reason why is right here on the back of this slide. We've been burning fossil fuels, which add carbon dioxide to the atmosphere, and this is trapping extra heat. Now, how does that happen? Well, extra heat is actually added to the atmosphere when sunlight passes through the atmosphere. It actually warms the surface of the Earth, and that warm surface sends heat back out towards space. But as the heat goes back towards space, it's actually different than the light coming from the sun. The light coming from the sun is in the form of visible light, and it goes right through the atmosphere. But the energy that heads back out towards space gets stuck, and the amount that gets stuck depends on how much carbon dioxide there is in the atmosphere. So if we trap this extra heat in the atmosphere, if we add carbon dioxide to the atmosphere, we trap the extra heat and keep it from leaving back out towards space. So what happens to the heat? Now, I said at the beginning I'm an oceanographer, so you probably have a hint, but you may not realize just how big an influence the ocean is on our planet's climate. And this chart is a stark reminder of just how important the oceans are for understanding what's happening to our planet. Over 90% of the extra heat that we're trapping with the greenhouse gases is warming the oceans. Now, the very first graph that I showed you showed that the atmosphere is warming up. But in fact, the real action, the real place where most of global warming is occurring is in the oceans. And you can think of the atmosphere as sort of like a piece of aluminum foil wrapped around a potato in the oven. If you reach into an oven that's 350 degrees and you grab a piece of aluminum foil, it actually won't burn you if it's all by itself, because the aluminum foil can't carry that much heat. But if you wrap it around a hot potato, then you're in big trouble. And the oceans are sort of like the world's heat potato. They trap over 90% of this heat, and they can absorb heat very quickly and very efficiently. So really, when we think about global warming, we should be thinking about ocean warming, because that's where most of it is happening. Now, as the planet warms, we see effects all over the world. The oceans are warming, the air is warming, and as this happens, we can see that ice around the planet is actually melting as well. And if you look at the black and white picture here, this is a picture of an Alaskan glacier taken in 1941. And you can see the ice running through this canyon as it snakes around between mountains. But in 2004, someone went back to the exact same spot and took the exact same photograph, and you can see that the ice has now retreated far into the canyon, many miles into the canyon. And this is something that's actually happening all over the planet. Over 90% of all the glaciers in the world are retreating and getting smaller as the climate warms. And as that happens, it actually raises sea levels around the planet as well, because the ice that's lost from the glaciers runs off into the oceans and adds that extra water to the ocean level, raising sea levels everywhere. Now, we know that sea levels are rising for some really interesting reasons. And one of my favorite plots, one of my favorite graphs, I told you I wouldn't show you too many graphs, but I'm going to show you a couple more. But one of my favorite, most interesting records is this record of sea level change from North Carolina, along the coast, collected in a salt marsh. And this is one of my colleagues who went out and they drill holes through this salt marsh and dig up the mud, and it gives them a record back in time of how high sea level was along the North Carolina coast. And if you look back at the record, you can actually see that from the year 0 to about 1000, sea levels really were not changing in the Atlantic Ocean. They were very stable, and that's because we had reached a warm climate and sea levels had stopped rising after the end of the last ice age, and they were really very stable. And then about 1000 AD, we entered what was called the medieval warm period. And this was a period where there was a little bit of warming and there's a little bit of sea level rise you can see right here. After that, in about 1500, there was the Little Ice Age where there was a small amount of cooling, so maybe sea levels fell just a little bit. But what really leaps out in this record is the beginning of the Industrial Revolution. In the 1850s or so, we began adding a lot of carbon dioxide to the atmosphere. We began heating up the planet, as you saw in the very first slide, and sea levels began to take off and rocket upward. And the salt marshes, which are shown there in the red curve, actually tell the same story as the tide gauge, which goes back over 100 years nearby in this location. And they both show that sea levels were rising very quickly after the Industrial Revolution began. So what's happening to our oceans is something that hasn't happened in thousands of years. And it's a reminder of just how big an impact we're having on the climate. Now, of course, I've talked a lot about climate change, but where is NASA in all this? Well, NASA actually flies satellites that measure sea level directly. And this is the Sentinel-6 satellite. It works in a very simple way. It bounces a radar off of the ocean and measures how long it takes to go down and come back up. This tells the satellite how far away the water is, and then using positioning systems like GPS and a couple of others, we can tell where the satellite is. So if we know where the satellite is and how far away the water is, we can say how high the water is, how high sea levels are everywhere in the world once every 10 days. And this gives us a really powerful tool for measuring sea level rise, and one that we've actually been using for almost 30 years now. But as we heard at the very beginning of the program, our latest sea level mission, Sentinel-6 Michael Freilich, was launched on November 21st, 2020. And this is actually the most accurate mission to date to measure global sea levels. It'll give us all kinds of really fascinating information, but one of the most important things is it's the satellite so nice we built it twice. In fact, there's two Sentinel-6 satellites. The Sentinel-6 Michael Freilich was launched last year, and in 2025, an exact copy of the satellite will launch and replace the Sentinel-6 Michael Freilich satellite. So each one will last 5 years, giving us a 10-year extension to our record of sea level rise, which goes back to the early 1990s. Now, the launch of Michael Freilich was kind of exciting because it launched on a rocket that went up, but the rocket actually came back down and it landed on the same launch pad it took off from. I was there and it was kind of an exciting day because when the rocket came back down, it's going faster than the speed of sound, so it creates a sonic boom, and I happened to get a little video of it where you can hear the sonic boom. So if you're listening to this really loud, you may want to turn your volume down a little bit. Here we go. Check out this video. Well, it wasn't just the rocket that made a boom that day. In fact, Sentinel-6 Michael Freilich was a huge boom for advancing our knowledge of sea level rise. And the fact that it launched successfully was incredibly satisfying. And in fact, we've gotten the very first data back from it, was released in June publicly. This image shows the height of the oceans in the Pacific and a little bit in the Atlantic. Red is higher than average by about 10 or 20 centimeters, and blue and green are a little bit lower than average sea level. But what you can notice is actually most of the globe is pretty red. That's because sea levels have been rising now for about 30 years. And I mentioned that Michael Freilich, the Sentinel-6 Michael Freilich satellite, was part of a set of missions that go back to the early 1990s. And this slide gives us a sense of just how lucky we are in the oceanographic community and the climate community to have had a series of satellites that go all the way back to 1992, which starting with Topex Poseidon, which is actually the satellite that got me my PhD. That satellite and its successor, Jason 1, Jason 2, and now Jason 3, have overlapped from one after the next, going all the way back to 1992. And that overlap's incredibly important because it gives us a continuous record of how sea level's changing that is incredibly accurate. In fact, it is so accurate that we can measure the rise of the oceans with an accuracy of just about half a centimeter, that's about a quarter of an inch, once every 10 days. And so every 10 days we get this incredibly accurate look at the average height of the entire planet. Now that's a huge feat because remember, more than 2/3 of the planet's surface are covered by oceans. So as we watch the sea levels change globally, we're literally watching how the Earth is reshaped one week after the next. And when we look at the data, you can see right here this up and down that happens every year, this sort of rise and fall in global sea level. And this is actually due to the exchange of water between the oceans and the land. Every year in the summertime, in the northern hemisphere, the ocean evaporates lots of water up into the atmosphere and it rains down over land. It takes that water some time to reach the ocean again, and during that time, sea level actually falls until the water begins to run back off. The seasonal cycle shifts to the southern hemisphere, and sea levels begin to rise again. So this rise and fall of the oceans, which is about a centimeter every year, or about half an inch, that is sort of like the heartbeat of our planet. It's like the exchange of water is really telling us how our planet's changing in an incredibly detailed way. But what's fascinating, really, to me, is that if you look at this record that goes back from the early 1990s to today, the most visible part of it, the thing that jumps out at you the most, is the steady rise of the oceans. And I say steady, but it's actually really not steady because the rate of rise has increased, and you can almost see it in this curve. But in the early 90s, the rate of rise was about 2 millimeters per year. In the 2000s, it was 3 millimeters per year. And today, it's between 4 and 5 millimeters per year. So we're literally watching the rate of sea level rise increase from one decade to the next. And it's satellites like the Sentinel-6 Michael Freilich mission and the Jason missions before it that allow us to do this. Now, I want to shift gears just a little bit here and talk for a second about the causes of this rise. And one of the reasons we're seeing this increase in sea level is the melting of the ice sheets. Now, NASA has another neat tool in collaboration with the German Space Agency. It's called the GRACE mission, or now the GRACE follow-on mission. And this satellite is actually a pair of satellites. These two satellites chase each other around the Earth. Their names are Tom and Jerry, in fact, just like the cartoon characters. And whenever the first one goes over something heavy, the pull of gravity causes it to speed up and move away from the second satellite just a little bit. So what we do is we measure the distance between the two satellites very, very accurately. And by watching them move together and apart, we can infer how heavy the things are that we're flying over. So, for instance, when we fly over a mountain with this satellite, we see the satellites pull apart at the beginning and then come back together when the mountain is between them. So using this information, we can literally weigh the continents. And when we weigh the continents or the islands like Greenland that are covered in ice, we see that the ice in Greenland is actually disappearing. Now, this animation shows the ice beginning to disappear, and you'll see the red start to appear around the edges of Greenland. That represents tons and tons of ice that are being lost from the edges of the ice sheet. And during the last 15 or so years, Greenland has lost 5 trillion tons of ice, and that's enough to raise sea levels by more than a centimeter, almost 3/4 of an inch. So this rise that we're seeing in the oceans is directly driven by the loss of ice in the great ice sheets like Greenland. Now, before we get too deep into Greenland, I'm going to shift gears again, and we're going to talk a little bit about a mission that I helped propose about in 2014, many, many years ago, called Oceans Melting Greenland, or OMG for short. And I'll show you just a quick little video to give you an introduction to what that mission's all about. There's enough ice here in Greenland to raise sea levels by 25 feet all the way around the world. It's an incredible amount of ice, and it's melting and adding to sea level rise. For Oceans Melting Greenland, what we really want to do is measure the oceans, measure the ice, and watch them change together year on year, and try and answer the question, how much are the oceans melting away the ice, as opposed to the air, which is what most people have studied so far. It's really a breathtaking landscape. These giant mountains and canyons are all along the coast. When you look out the window, you really get a sense of just how huge these glaciers are, these gigantic rivers of ice that are draining the ice out of Greenland into the ocean. And then they reach the ocean, and it gets all broken and craggy, and big chunks fall off. It's incredibly dramatic. Kulasuk is just a tiny little town in southeast Greenland, and we've been launching probes out of here for the past 4 or 5 days. It's already been a fantastic year for OMG measuring the oceans. We launch them right out of this tube right over here. Open up the tube, you can look right down it and see the water passing by, or sometimes the icebergs or clouds or whatever it is we're flying over. We slow down a little bit, and we just push these big gray cylinders out of the bottom of the plane, and they fall to the ocean and measure the temperature and salinity when they get there and radio it back to the plane. We're really trying to look at the ice and ocean all the way around Greenland. So we're dropping 250 profilers. We're going to cover the coastline all the way around. And in the spring, we map out the glaciers with a radar, also all the way around. So we're really looking at mapping all of the ocean ice interactions in Greenland as best we can with one mission. So there's a little information about Oceans Melting Greenland, or OMG for short. And as you're probably wondering, yes, I did come up with the name OMG, in part because I wanted people to remember how surprising it is that we're having such a big impact on Greenland, but also because those 3 words really embody what the mission's all about, which is that the oceans are playing a big role in the ice loss in Greenland. So we started out really thinking about how the Earth was warming, and the oceans reminded us that they play an enormous role in how the climate's changing. Well, Oceans Melting Greenland is zooming in on how they're changing the ice in Greenland. Now, the idea behind OMG, as I said in the video, was to measure both the oceans and the ice and try and understand how changes in the ocean could lead to changes in the glaciers all around the edges of Greenland. You're probably also wondering if I'm wearing the same shirt as I was in that video, and yes would be the answer to that question. So let's take a little deeper dive into the process that allows the oceans to reach in and melt these glaciers. Now, we normally think of Greenland as melting from above, like a big ice block under a hairdryer. But actually, the ice on Greenland is sliding off into the ocean in the form of these glaciers. And if we look at how the glaciers are changing, we can actually get an idea of why the oceans might be playing such an important role. Now, many of the glaciers in Greenland reach right to the sea, and as melt from the surface accumulates on the ice, it actually drills a hole down through the glacier, and it allows the water to run underneath the glacier along the glacier bed. This meltwater, when it reaches the ocean, it's actually very fresh, which means it's much lighter than normal seawater. So this fresh water begins to rise up the face of the glacier. And as it does, it runs into a very interesting situation because the water around Greenland is warm down deep. It's warm in the deep parts because that water is salty and from the Atlantic Ocean. Now, as the water rises up the face of the glacier, it actually eats away at the bottom and eventually breaks off a chunk of the glacier in a process called calving. And as calving increases, then the glacier can actually retreat, and if it retreats, it speeds up, dumping more and more ice into the ocean more quickly and driving sea levels higher and higher. So the ocean temperature, the water that's actually reaching up towards the glacier and warming it, is actually really important for the speed at which the glaciers calve off and the rate at which they speed up and dump ice into the oceans. So that's sort of how the oceans can affect Greenland. And for Oceans Melting Greenland, this was an airborne mission. So we used airplanes to try and understand these two questions. And we flew the airplanes around for 2 different surveys each year for 4 or 6 years in the case of the ocean. For the ocean part of the survey, we dropped those cylinders out of the airplane. They fall to the water and actually split into 2 parts. One part stays at the surface and radios the data back to the plane, and the other part falls down connected by a very thin wire and measures the temperature and the saltiness as it goes. The ice survey looked at how the ice edge changed with a radar. So when we looked at these things together, we tried to understand how changes in the ocean could lead to changes in the ice, and our records really showed us that the oceans are playing a huge role in how quickly the ice retreats. Now, one of the things we saw were really beautiful scenes like this one, which show the ice edge with a large plume. This is what the plumes actually look like in real life when they reach all the way to the surface. We flew past this plume and dropped a sensor into it, measuring it all the way down to the seafloor. It was a very exciting day. Now, these plumes, as you can imagine, are important places for us to measure. And this year, when we were in Greenland in August, in September, we found a single plume on a very big glacier in East Greenland. And this picture on this picture here with the blue plume pointed out, the plume pointed out in blue, is actually a satellite image that I saw the day before we got in the airplane and flew all the way across the ice sheet. And we did this just on the basis of this picture, because in that tiny plume, we realized that there would be water coming up and reaching the surface, and it was an opportunity to measure the oceans right next to the glacier edge. When we got there, what we saw was here, where you can see this huge open area of water, which is about 300 feet across in diameter, right next to the ice edge, which is a couple 100 feet tall. So it was an incredibly beautiful thing to see, but one that we were actually able to measure because we were able to use satellite images like this one and get from one place to the other across the ice sheet with our really cool looking airplane, which was a DC-3. Now, we also got to fly around and see neat things like icebergs. which you can see here in this flyby. You'll notice as the wingtip goes by, the iceberg is actually higher than our wingtip. So some of these things are really enormous, and it's a reminder of just how much ice is coming off of the ice sheet, which is important for sea level rise. Now, in the first couple years of OMG, we actually measured one of its biggest glaciers and found that this glacier was actually growing. This was a big surprise because Greenland's fastest moving glacier, called Jakobshavn, had actually been in retreat for about 20 years. Now, Jakobshavn is on the western coast of Greenland, and it's next to a huge bay right here. And inside this long fjord, right where the pointer is right now, is the edge of this mighty glacier, which is known locally as the Ilulissat Glacier. Now, this glacier is famous among glaciologists because it's been retreating so fast, but in the first year of OMG, or the first 2 years of OMG, we found that the glacier was actually growing. And these images, which were taken by our aircraft measuring the glacier, show in blue where the glacier was actually getting thicker from one year to the next. And this happened from 2016 to 2017, 2017 to 2018, and 2018 to 2019. So why was it getting thicker? Well, it turned out the answer, much like all the answers to the questions in this talk, was the oceans. When we looked at the oceans nearby in this bay, in Disco Bay, we found that the oceans had cooled down after decades of being almost 2 decades of being warm. The waters in front of this glacier actually cooled off. And when they cooled as part of a natural cycle in the Atlantic Ocean, the glacier began to grow again. So OMG essentially proved its major hypothesis, which was that the oceans are playing a huge part in controlling how fast the glaciers are retreating. Because when we saw this particular glacier react so strongly to the oceans, we knew without a doubt they were playing a big role in Greenland's ice loss. Now, if you'd like to learn more about OMG, you can check out the OMG webpage at omg.jpl.nasa.gov. You can see yet another picture of me wearing this red shirt and watch all the fun videos that I showed so far. Now, before I wrap up, I want to talk about one last thing, which is the future of these kinds of missions to study sea level. And at NASA and in collaboration with the French Space Agency, CNES, and also with the Canadians and the British, we're hoping to launch in 2022, late 2022, the next revolution in sea level measuring missions from space. This is called SWOT, which stands for Surface Water and Ocean Topography. And essentially what it will do is look down and measure sea level, but instead of measuring it in one small spot and taking 10 days to fly around the world and cover pretty much the entire oceans, SWOT will measure an entire swath of the ocean all at once as it flies by. And this will sweep out a much finer look at the oceans. You can think of it as sort of like turning in your old standard definition TV and getting a high definition TV, or maybe even a 4K TV. SWOT will allow us to see very small structures in the ocean, allow us to see sea level as it changes right up next to the coastline, and really be a powerful tool for measuring how the oceans are changing their shape over time. It's exciting too because it will also allow hydrologists, folks who study water on land, a much broader look at lakes and rivers all around the world. So it's a really exciting mission coming down the pipeline. It'll launch in 2022, and we're all really excited about it. And with that, I will stop and be happy to answer some questions.
Yeah, absolutely. Josh, you've given us a ton of information, and I'm sure we've got a ton of great questions out there. So, Jocelyn, what are they asking us?
Yes, we do have a lot of really great questions coming in through our social media. The first one, let's kick it off with Filanka on YouTube wants to know warming of the planet is natural, right?
Well, that's a great question. A lot of people want to know how much of the current warming of the planet is part of a natural cycle. But if you remember back at the beginning of the talk, the planet was already in a very warm period. And what's happened in the last 150 years has been warming on top of that already warm period. So the warming that's happening today, the warming that's happened since 1850, that's almost entirely human caused, and it's driven by adding fossil fuels to the burning fossil fuels and adding carbon dioxide and other greenhouse gases to the atmosphere.
Great. And JB Maps on YouTube has a great follow up question to that. They want to know, does NASA keep up with all the underwater volcanic activity going on? And does the volcano have anything to do with oceans heating up?
Well, that's a great question. There are sources of heat in the ocean from down below. There are underwater volcanoes. There are things like hydrothermal vents. But when you compare the amount of heat that comes out of all of those volcanoes and vents all around the world with the heat that we get from the sun every day, it's really, really tiny, way too small to be a major impact on today's warming. So, do we track every volcano from space? We don't track every volcano from space, but we do know about how many there are and about how much heat is coming up. And we're pretty sure that it's way too small to be a major cause of today's warming. Not to mention that if you look at the planet, it's warming from the top down and not the bottom up.
Interesting. And now switching gears to a little bit about your time out in Greenland with OMG, DT on YouTube wants to know what kind of aircraft does the team fly with?
Oh, that's a great question. We actually fly with for the last few years, we've been flying with an old DC-3 aircraft that was modified and more or less rebuilt to carry out science in the Arctic. And these old planes are really neat. The pilots call them tail draggers because when they're parked, they're sitting on a slant. The rear tail wheel is much smaller than the main landing gear. And so when you take off, you're already tilted up, and then the tail comes up like this and you take off. And when you land, the opposite happens. The main wheels come down and then the rear wheel goes down. So you tilt back up almost like you're taking off again. But they're really, really neat planes and fantastic tools for science. And OMG benefited enormously from being able to use them.
Amazing. And I know that you get a lot of great data from up there. Mike on Facebook wants to know how much uncertainty is in the measurements, plus or minus, what's a rough estimate?
Well, of course, with any measurement, the uncertainty depends on what it is you're trying to measure. So when we're talking about things like global sea level rise, for example, every 10 days we get an estimate of the average height of the oceans with an error bar, an uncertainty of about half a centimeter or a few millimeters. Now, we get many of these per year, so if we average together a year of data, we can really say how high the oceans are from one year to the next with an accuracy of just a millimeter or so. And that's what allows us to see the rise and fall of the oceans that I talked about with the exchange of water between ocean and land, like the heartbeat of the planet. But it's also what allows us to see the increasing sea levels caused by the warming of the planet with really a fantastic accuracy.
Interesting. Dan Cooper on YouTube is asking, don't the oceans absorb most of the carbon dioxide as well?
That is a really great question. The oceans absorb a lot of the carbon dioxide. It's between a quarter or a third, something like that, depending on how long a period you look at. But it's important to remember that the CO2 is not just staying in the atmosphere. A big chunk of it is being absorbed by the oceans. And that means that even if we were to somehow, which would be very difficult, take carbon dioxide out of the atmosphere, some of what we added to the oceans could come back to haunt us. So we're not just adding CO2 to the air, we're adding it to the oceans, which also makes the oceans more acidic. And this has a big impact on marine life and marine ecosystems, and one that we're really just beginning to understand.
You've given us so much great information about sea level rise and how it's happening. And looking to the future, TKO Scar Loves on YouTube wants to know, what do you think will happen to the future at this rate with sea levels rising?
Well, one thing that's clear is that sea levels are going to continue to rise for a very long time. The warming that we've already caused is going to continue to raise sea levels at a slow rate for up to thousands of years from now. So we're looking at continued rise, but the question really is, how much rise do we want to allow? And some scenarios are feasible where we could have many feet of sea level rise in the next 50 or even more in the next 100 years. And if we allow that to happen, it would really be devastating to millions and millions of people along the coast. In fact, every centimeter, or about a half an inch, of sea level rise affects another 3 million people worldwide, with increased frequency of flooding, erosion of coastlines, and damage to infrastructure. So it's really a creeping problem, and one that's not going to go away anytime soon.
Well, Josh, thank you for answering those wonderful questions and for sharing this very important information for us. Unfortunately, that is all the time we have for tonight. I want to thank you, Josh, as our speaker, Dr. Josh Willis, for your insight and excitement tonight. I also want to take a moment to thank you, Jocelyn, for being our wonderful co-host, and for all the people behind the scenes who really make these talks possible. And finally, a big thank you to all of us who join us every month for these wonderful talks. Please remember, you can watch past Von Karman lectures on JPL's website or YouTube channel. As this is the final lecture of 2021, we hope you have a happy and safe holiday season, and we will see you next year for our January talk, where we will continue this conversation with the Surface Water and Ocean Topography Mission, or SWAT. Thanks again for joining us this evening, and we'll see you in 2022.